Saxon Advanced Mathematics, lesson 122. We are on lesson 2 of our bonus lessons here, zooming toward the end of the book. This lesson has 2 parts, but they're related. And it seems a little wild at first, but I think you'll be able to bend your mind around this topic fairly easily. What we're going to be doing is graphing rational functions. Okay, that is going to look a little crazy, but we have some simple rules to break it down. Let's get right into our example so we can see what we've got. We're supposed to graph this. I know. It's a lot, isn't it? How in the heck are we supposed to graph that? Well, it's going to look crazy. I'll tell you that right now. But when we have it factored, when we have our function factored like this, it's going to make it easier to understand. The numbers in our numerator, we are going to call the zeros. And what we're going to find is that our graph is going to cross the x-axis at every 0. Okay, I'll repeat that to you as we go so you don't have to write it down now. But these numbers we'll be able to call our zeros, and they will create the crossing points on our graph. These numbers are called the poles. Now, as you can quickly see, there are certain values that we cannot let x equal because we would then get a 0 in our denominator and we would blow up the kingdom and it would be really bad. So we can see that -5, -2, +2, and +5 are all going to be problems, and what we're going to do is create asymptotes. We're going to create those dotted lines that the graph cannot cross. And so we will create jumps in our graph for every one of the poles. That's kind of weird, right? Well, let's take a look at how this particular graph would look then. Okay. I think I want to go up 2, 3, 4, 5, 6. Ooh, I just have enough space. Oh no, it's not going to be big enough. Never mind. I'm not going to do it. I was thinking about doing it every other, but that's not going to work. So I'll just use my grid. Okay, so the zeros of our equation, we simply set, we can do it mentally. We take each one of these terms and we set it equal to 0 and solve the algebra if we need to. So this first one says that x equals 0. So we're going to put a dot right here at the value of x equals 0 because that's one of the zeros of our equation. This one, x minus 7 equals 0. When we do the algebra, that means x equals +7, and that means 1, 2, 3, 4, 5, 6, 7. Here's another place where our graph will cross the line. So that's very useful information. I only put the hash marks in the first quadrant. That doesn't mean anything. I was just counting out the spaces. So these are our 2 zeros, and we put dots on the x-axis at the value of our zeros because our graph is going to cross the line there. All right? Now we need to graph our poles. And again, we just set these equal to 0, and we know that those are numbers that cannot appear on our graph because they would create zeros in one of these factors and they would blow up the kingdom. We'd have a 0 in our denominator. So now we're going to graph these, not with dots, but with asymptotes. And I'll remind you what those are. So x plus 5 equals 0. We can't let that happen. So x cannot be equal to -5. 1, 2, 3, 4, 5. Right? So we can't, I'm not putting a dot there. What I'm doing is just marking it, and then we're going to mark it with an asymptote. We cannot let our graph touch at x equals -5, because then that would give us a 0. Big problems. Likewise, x cannot equal -2, because then that would come to 0. So we're going to create another asymptote at -2. Okay? So at the zeros, we put dots. Now we see, oh no, that was just my dot where I was getting organized. So this is a dot and this is a dot. I'm going to recircle them so you can tell that they're intentional dots, because I'm making other dots just as I get my markings organized, and I don't want you to be confused. Okay, so we've got the first two poles graphed. X -2 equals 0. Well, that says x cannot equal +2. And then x -5, that says x cannot equal +5. So that would be here, right? So these are our zeros, and these are our poles. X cannot equal -5, x cannot equal -2, x cannot equal +2, and x cannot equal +5. That's where I get all of those. This is x equals 0. Let's see, I'll write those up on top. Where am I going to have room? I'll write it right here. X can equal 0. We're allowed to have zeros on the top. It just creates a crossing place. And then this is x equals 7. Okay, so now we've got some key places marked in our graph. The zeros give us what are going to become crossing points. The poles give us no-fly zones. I often think of our no man's land. We cannot let our graph cross over those dotted lines. So, how are we going to actually draw the graph? We've got some. We've got some guides in place. But in order to actually graph this, we have to start over here. And what John says, and this is the one place in this problem where I am not sure how to explain why this is true. John says that if we look at the largest terms for the numerator and the denominator, so essentially if we multiplied these out, this would become, I would say it would become x squared, right? Because we'd have x squared minus 7x if we multiplied that. But John says this is minus x squared. I don't know how he gets that, because there's a minus sign, but that wouldn't affect this. So let's just assume his minus sign is right, and I will continue to do some research on why that is so. In the denominator, we would have 1, 2, 3, 4 x's, wouldn't we? So this would be x to the 4th. So what we would have here is a negative fraction. And as we chose values for x that get bigger, this fraction is going to get tinier, right? Because as we square these and raise these to the 4th power, this is going to get bigger faster than this. And so that fraction is going to keep getting smaller because the denominator is going to expand faster than the numerator, because this is a 4th power and this is a squared power. So it's going to be getting more and more out of proportion, right? These numbers are going to get farther and farther apart as x gets bigger. So as x gets bigger, the negative fraction gets smaller. So what that tells us is that the way it's going to behave out from this this is our farthest point to the right. What it tells us is that our curve is going to become a horizontal asymptote. It's going to become closer and closer to this. It's going to stay on the lower side of this line because it is negative. Again, that makes no sense to me. If you understand why that's negative, tell me. Send me an email right now. But I don't understand why this is negative, because that looks like a positive pair of x's to me. But in any case, let's just assume that it's correct that it is a negative. And so that's why it's below the line. If it was positive, as I expect it should be, it would be just above the line. Now, how do we continue to graph this? In order to graph this curve, we see that this has to go up, right? Now, we said that the poles are places where the graph must jump across, is what we said, which is kind of a weird expression. What do we mean by that? We mean that if it's going up here, then it's coming from the negative down here. It's kind of like it goes up to the end of infinity and comes around back to the other side. I know that makes no sense. But if it's going up here, then it's going to come in from the other side down here. Now, our line is moving up, right? We're going to point it down because that's how it like looped around. And within these two asymptotes, we see there's no crossover point up here. So what that means is that our graph is going to turn around and go back. What the actual heck? So now it's going down, so that means it's going to come in from the top over here. And I'm going to use another color to help you see that. Now, within this pair of asymptotes, we have a crossover point. So our cute little graph is going to go over there, it's going to go through there, and then it's just going to keep going down. Okay, so let me just highlight this. It went off the graph going up, and so it comes back in from the bottom, right? It turns around, it goes back down. So now it's going down, so on the next section, it comes in from the top, and I'll put an arrowhead on there so it looks the same. Do you see how the graph jumps, right? It's heading down, so it comes in from the top. All right, now this one's coming in from the bottom, and so it's going out the bottom, so it's going to come in the top, like so, but there's no dot here for it to cross the line, so it's going to do the same thing. It's just going to turn around. And how much space we give it to turn around, that's not important. Just eyeball it and make it interesting. Okay, this one went out at the bottom, so it comes in at the top. Notice how they're always opposite each other. And then this one goes out the top, so it comes in at the bottom. And then we're just going to let that trail off. We don't know what that does because we don't know, is there another asymptote? There isn't. There's no other asymptotes or crossing points. So presumably that's just going to continue on in that direction. So this one went out at the top, and here it is coming in at the bottom. When I first learned these, I got confused because it seemed to me, yeah, it's going out at the top, but this arrow made it look like to me, oh, it's going out at the bottom. Remember, this arrow doesn't indicate direction, it indicates infinity, right? It says it's always going to keep going. But you can think of the line as moving in this direction as well, right? It's going out here, so then it comes back onto our graph from the bottom. So as you're moving between the asymptotes, think about the way I've indicated the colors here. If you go out the top, then you come back in at the bottom. All right? This is the final answer of our graph. That's kind of intense, isn't it? The most important thing I want you to understand is that the numerator gives us zeros or dots that we want our graph to pass through. The denominator gives us what we call our poles, and that's where we set up the asymptotes because we can never let our graph touch at those places because we don't want to blow up the kingdom. All right? We're going to come back to this in the last example in this lesson. And this is really kind of the trickiest part, I think, is just trying to think a little bit about how your function will behave going to the greater values of x, right? Because this is the x-axis, so this way they're going bigger. But simplifying our function to just look at, these are the highest degree terms. That will help us understand a little bit about how that's behaving. And spoilers, ours are either a negative asymptote or a positive asymptote. It could be too. So We'll look at another problem like this in just a minute, but let's go on to our second topic, which is, it's got a frightening name, but it's actually pretty straightforward and cool. Graphs that contain holes. What? Sounds terrifying, doesn't it? Let's dive in. And we're going to start by graphing something much simpler than what we just did, so it'll make more sense to you. Graph, although it doesn't look like it at first, graph y equals minus x squared minus 5x minus 6 over x plus 2. Notice that we've slipped away from our functional notation. That's okay. We don't have to use functional notation in order to understand that this is a function also that can be graphed. So that's what we're going to do. Okay, the first thing we noticed is that x cannot equal 2. Right? When we go to graph this, this is what we would call our pole, right? We only have one in this one. It's our pole. We cannot let x equal -2. Let's go ahead and factor the top, though, and see what we get. What I'm going to do is I'm going to pull out a -1, and that will give us x squared plus 5x plus 6, and that'll all be over x plus 2. And now I can factor this by inspection. I can write y equals, I'm going to drop the 1, I'm just going to put a minus sign here, and then it will be what? X plus 3 quantity times x plus 2, right? These two multiply to 6 and add to 5. Yippee-yi-yay. And then we'll put it over our old friend here, x plus 2. And now look what we can do. We can cancel those. Y equals minus quantity x plus 3. This does not look graphing friendly, but if I reincorporate the minus sign, if I distribute that back across, I'll have a y equals mx plus b format, right? So I'll have y equals minus x plus 3, and I can squeeze in a slope of 1 over 1 there. So this is y equals mx plus b format. We're ready to graph. Okay, you might need a little refresher on how to graph because this is so old and basic that it might be hard. We start with the y-intercept. We go to that. Oh, you know what? When I distributed wrong. This should be a minus, shouldn't I? I need to hit them both. So we go to -3. That's where our y-intercept is. And then our slope is -1 over 1. So we know that that means we go down 1 and over 1. There's our second point. So we know that the solution to this function is going to be this line, but we said way back here in the beginning that x cannot equal negative, it should be -2. I'm sorry, I'm making little annoying mistakes, aren't I? It can't be -2 because x plus 2 cannot be 0. You were probably confused when I wrote that. I was wrong, it should be -2. So what that means is that at no point, right? It's not just here, but we cannot let x equal -2 at any point. So when I go to draw my line, it's going to look kind of like this, right? I cannot let it touch at -2. Right? So I'm going to just turn my paper so I can freelance it a little bit, and I'll show you how I will do it for practical purposes. Okay, I drew my line, but now I'm going to eyeball this and go, okay, this is -2. This little part right there, that cannot be on the line. So this is my graph, but it has a hole in it. There's a little hole right there where we have to skip that value where x equals -2. That is a pole, but because our drawing is more simple, it's now become a hole. What? It turned from a pole to a hole, right? So that is how we take this limitation into our picture, and this is the right answer. Crazy, right? Okay, so this was our easy one. This was just a linear drawing. Now we're gonna go back. We're gonna do another one of those crazy big problems, and this one will have a hole in it as well. Okay, so I'm gonna keep these notes handy because we may need to look at those again, right? This is example 122.3. This is our final example for this lesson. All right, here it comes. It's a big, crazy thing. Copying, copying. There are a lot of quantities, aren't there? Thankfully, we don't have to factor this monster. Okay. So we remember that the top are going to be our zeros and the bottoms are going to be our poles. But before we get into that, you may have noticed as we were writing this, we have the quantity the same, top and bottom. So we can cancel this. It's not going to be a zero and it's not going to be a pole, but we still have to say x minus 1 cannot equal 0 or x cannot equal 1. I got the sign right this time. We have to remember this because we have to make sure our graph, even though this quantity is not going to show up as one of our poles, we're not going to have an asymptote at minus 1. We're going to have to create a hole at minus 1. That's what it really boils down to. When we cancel it, it no longer lives as an asymptote, but we have to give it life as a hole now. Okay, so let's draw ourselves a big fat graph. And let's go ahead and practice putting in the zeros. And remember, those we mark with dots. And these are the poles. And these we mark with asymptotes. Okay, so our zeros will be, remember we just take the negative, the opposite sign. 1, 2, 3, 4, 5. There's going to be one of our zeros. Positive 3 is going to be another 0. And then this one we've canceled, so we don't have to worry about it. Now for our asymptotes, this is going to be positive 4. 1, 2, 3, 4. So we're going to have one right here. And then we're going to have one at negative 2. And then we're going to have one at negative 4. And then that's all, because we canceled that one. Okay, negative 4, negative 2. So this is x equals negative 4, x equals negative 2, and then this is x equals 4. So there are the way our three poles translate to the three asymptotes. This is x equals minus 5, and this is x equals positive 3. Those are our two zeros. So we first worry about setting the way the curve looks here. And we can see that if we just look at the largest degrees of our terms, we'll have y equals, it'll be x squared over 1, 2, 3, x to the third. So again, as x gets larger, the function gets smaller. So we're going to have that same horizontal asymptote that's going to work like this. But then as we go here, it will go up. Okay? Now we're ready to start that process of tracing the loops back, right? So we went out on this side of the asymptote out the top. So this one will come in the bottom. And we do have a place to cross here. So this will come up and then it will go over like so. Those asymptotes are not perfect. Okay, so this yellow one went out the top and it came down here at the bottom. It went up. That wobbles back in. Don't take that too seriously. That one goes out the top. Comes back in the... Oh, wait, this should go over more. Right? This is just my 0 axis. I thought it was my asymptote, but it's not. So it goes out over here a little bit further. Then it goes out the top, so it comes in the bottom. It comes in, it looks up for the dot where it's going to change directions. There isn't one, so it says, okay, fine, I'm going back out. Right? Like so. So this is where our little pink guy comes in. And then this is where he says, no, I'm leaving again. And then it comes back in the other side, crosses the 5, and then it goes out. If these front ends confuse you, the front and the back ends is how I think of it, the right and the left side. I don't want you to worry too much about that. That's the most confusing thing about this. If you can kind of get how we use the zeros and the poles to guide the graphing, and then we do this thing of wherever it goes out, it comes in on the opposite side. It either crosses through a 0 or it says, yikes, I don't have any zeros, I'm gonna have to just leave. That's the main thing I want you to get. This graph, though, has one more detail we need to fill in because we said that x cannot equal 1. So what that means is we have to go back in and we have to create a hole at x equals 1, wherever that shows up on our graph, right here. This technically is not that's not a solution to our function because that would blow up our denominator also. So again, if I could erase that little bit of line, I would, but in terms of just being practical and how we write out the problems, it's okay to just create a hole over the top. So this x minus 1 term that we canceled gives rise to that hole. Okay, so that's how graphs can contain holes. That's lesson 122. I already crossed it off. 3 more to go. Thank you. Goodbye.